Welcome, everyone, to our very first Cosmic AI seminar. Thanks to those of you online who are joining us. We have a good in-person audience here. I'm going to talk about some of my work and motivation in terms of trying to identify features in spectral cubes. This is the very first seminar. So machine learning. Okay, so we mean by machine learning from data or data-driven intelligence. And usually, in addition to that, we mean some added statistical rigor or physics that has been incorporated into the model, right? So my motivation in this field has been to try to understand the star formation process better. Star formation is historically messy. It has a lot of physics. Young stars have a large impact on their environment as they're forming. For example, they heat and ionize their environment, blowing these large bubbles. They have stellar winds. Very young stars will also launch these very energetic collimated bipolar outflows like you see here. And as a result of all of this, star formation is quite messy, does messy things to the galaxy. Here we're panning along the galactic plane, and you can see all this very complex features here. This is warm dust emission, and you can see the bubbles right here that have been made by young massive stars. If you look closely, you can also see some dark regions. These are molecular clouds where stars are forming now. So if we look at these winds that are creating these bubbles a bit more closely and zoom on a particular region, this is the Perseus molecular cloud. It's one of these star forming regions that's relatively nearby to us. And so more than a decade ago, some astronomers looked at this region and visually identified these bubbles within the gas. And as a result of identifying them, they were able to add up the total mass, momentum, and energy associated with all of these features. And they found that the net effect, the total energy in these bubbles, was about half of the total cloud turbulent energy. So that is about half of the motions of the cloud were being made up by these stellar winds. This cloud also has some of these protostellar outflows in them. That's shown by the arrows. And you can see that that's much less of a contribution for this particular cloud. So this brings us to the point, well, this is super messy, but if we could just identify all of these features, if we just count them, if we can figure out where they are, then we could understand the whole problem of how stellar feedback works and how stars impact their environment. But there are several problems. So in the past, we've tried to do this using statistical approaches. By classical approaches, I mean pattern matching, peak finding, but this is really hard, particularly when your data is high dimensional. So the type of data that I often work with for star forming regions are spectral cubes. So these are cubes of line of sight information about what the molecules are doing within the gas. So for example, by the CO molecule is one we commonly run with. So problem number one is that these cubes are high dimensional and have a lot of correlation. There's no simple physical model. That is, there's so much physics in this problem, it makes things extremely nonlinear. The data are noisy, so we also have a low signal to noise issue that we have to deal with sometimes. Because we're looking at these regions with telescopes and they're far away, we have limited spatial and velocity resolution. In addition, we have instrument systematics. So there are actually features within the data that are due to the instruments, not the thing that we're trying to identify. Then the data are incomplete and contain complex biases. So in the real world, within this room, we have information about the full 3D spatial and 3D velocity information of all of our objects. But we don't have that information for regions in space. We usually only have a subset of that information because a lot of the emission is projected along the line of sight. So we're looking at averages of what is actually happening to the gas. So let me give you an example. So this is the B5 star forming region. So it's actually a spectral cube here. You're looking at position, and then along the line of sight is velocity and as it's rotating. You're seeing position and then velocity. And the things that are sticking out, those are high velocity features, probably associated with protostellar outflows from young stars within the gas there. As it rotates around, you're also going to see holes, and one hole there in the middle is due to stellar winds or radiation from a slightly more massive but young star. All right, so that means this data is very complicated, but if we combine together two things, machine learning and numerical simulations, then we can tackle 2 through 5 on this list. So we can build a physical model using numerical simulations. So because we're using these simulations, they can be complex, we can put in a lot of physics, and we can get the time-dependent behavior, which gives us lots of data. Let's see. In the room, it's not very visible here because of the lights are on. I don't know if you guys want to find the lights that is not on the screen here. All right. Yeah, so this is a simulation of a molecular cloud where there are some young massive stars blowing these large bubbles within the domain. Oh, now that's too, that looked much better. So here the red is hundreds of kilometers per second. These things move really fast. And blue is maybe tens of kilometers per second, and the gray is a few kilometers per second. So coming out of the simulation, we can't just use that to train our model. Instead, we have to make that data as similar as possible to the observational data. So we start with our simulation snapshots of the winds. We post-process them, usually using a radiative transfer code, to predict the emission that would be emitted by that gas. That is, we get the direct observables. Then we observe that emission as if it were coming from a real object at a certain point in the sky, and then we add noise and instrumental effects. And at the end of that, we have something that looks like an actual observation. So if we run enough simulations, we end up with a large, realistic set of physically based complex models with accurate labels. Then we take our training set and we feed it to a machine learning algorithm. That might be a little scary. There we go, that's better. Everyone feels more comfortable now. We feed it to a machine learning algorithm to be able to make predictions on real observational data. So when I was working on this 5 years ago, we first focused on slices of spectral cubes. So we built our model using UNet. This is relatively straightforward neural network architecture. It's been used for a wide variety of problems. So basically, we feed in our input data. It goes through a number of different layers. And through this process, we set all the weights because we have in our training set the exact labels for the things that we're trying to identify. So here's an example. So this is an example of some of the data that was fed in and test data set, and the prediction here are these pixels where the winds actually are in this data. To be more specific, we can color code the predictions based on whether it's the true positive, the pixels are right, false positive, incorrectly identified, or false negative, it's missing something. And you can see when we apply this to our test set, it actually does pretty good, right? There's a lot of blue. Most of the purple and green are on the boundaries of the things we're trying to detect. Now, it turns out when you apply that to spectral cube slices that are real observations, doesn't work so well. And the reason for that is because the stellar feedback, these winds and outflows, they have motions, they expand, they have connection across not just spatial information, but velocity information as well. So instead of doing a 2D convolution in the UNet, we switched to a 3D convolution, which connects the information across those full 3 dimensions. So we train it on our synthetic observation cubes, apply it to real data, and then compare to the previously identified detections. So this is an example of a real stellar wind bubble in the Taurus molecular cloud. That's another nearby star forming region. Also observed one of the CO molecule isotopologues. So here you can see the blue is the background cloud emission. The red is the identified shell, and mostly you see it's purple, which it means it's correctly identifying this feature. It's pulling it out of the background cloud. You can see it's doing a pretty good job. It's actually identifying stuff going all around that region and getting stuff above and below the cloud as well. So when we trained the model, we didn't just train one model, we trained two with two different purposes. So the first model, which we call ME1, trains on the total emission that contains some feedback gas. So if you were a human looking at the cube, you would identify a voxel as being part of a feature or not part of a feature. It's pretty binary. So this is similar to how human visual identification works. The second model, MF, or model fraction, instead of training on the whole voxel, is trained to predict the amount of mass in that voxel that's relevant to our identification. So it's basically learning the mapping between the emission in the input cube and the true feedback mass of the cloud that's part of that stellar wind that we want to identify. So we can run this again on some test data. Here's looking at mass momentum. Model ME1, there's open points above that, and then the one-to-one true mapping is shown in the dashed line. There's model MF. So the takeaway point here is this line of sight emission is a strong contaminant when we're trying to identify these features in clouds. As a result, if you do the human approach, use model ME1, you're overestimating the contribution of these stellar winds by a factor of 10. However, if you go to the second model, MF, you learn the correct mapping between the emission and the mass of the features, right? So you're basically getting the model to do some physics for you. You give it some input radiation emission, and then it predicts how much mass, momentum, and energy is producing that signal. So we did this again, but instead of focusing on these bubbles or winds, we focused on protostellar outflows. So here's B5 again. As I mentioned, it does indeed have outflows in it. So here's another study from more than 10 years ago. Here are the outflows identified by humans, particular human Hector Arce. He literally took this cube and scrolled through it and then found the things that looked like outflows. And as you can see, they're extremely blobby, very continuous, which is what makes this such a hard problem. However, with the simulations, we have the exact labels. We know where all the feedback is. We know where the outflows and winds are. So we can create a perfectly accurate training set that has these labels that identify exactly what we want. So here's an example application on a test set. So you have the input data, the CO integrated emission. Then you have our two models, and then the predictions that we get from our models. We can then apply that to the real Perseus data, and you get something like this, where, again, you have what is identified by each of the models, and then you have that overlaid on the total emission observed in this region. So in three-dimensional view, this is what that looks like. So you can see one of the reasons why it's hard is there's a lot of noise, a lot of complexity. And as I mentioned, there's a lot of confusion, right, between this sort of background gas where the stars are forming and these outflow features. The outflow features are the ones that are popping up below and above the blue region there. And so our model is able to correctly identify these features, separate them out from the background emission, and then make a correction to account for how much material is confused and is not actually part of those features. All right, so back to B5. Here's the same region with a different view. So each of those boxes is showing where the outflows are. As I said, they're very blobby. One of the reasons why it's hard to identify them. We identified two new outflows, which are shown here. The symbols are all where the young protostars are. And so this region at the bottom has a cluster of about 100 young stars, and as a result, very confused, a lot of messy feedback. So in this study, when we compared it against the previous work that was visual identifications, our model identified all 60 previously known outflows. We also identified 20 new outflows, which we checked by eye. And we are able to apply it to regions like this one, which are so messy, that are generally left out of visual studies. All right, so in summary, convolutional neural networks provide a fast, flexible, automated way to identify very complex 2D and 3D structures. The result of our algorithm, CASI-3D, produces a feedback map, not a catalog. So it doesn't necessarily segment it and name things, but it separates out the feedback from the non-feedback. So new outflows and bubbles, this is a new way to find them. And also at the same time, make corrections for observational biases. We know those biases are there, but they're very hard to correct for classically. But this is the question I often get, is how do you know your simulations and training set is a good representation of the real data, right? So there's a number of caveats in this kind of study. First, the underlying cloud conditions are uncertain. That is, we don't know what the underlying density, temperature, velocities really are for these regions. So that means we have to make a very large training set that encompasses all of the conditions that we think are a good representation of a particular observed region. Second, we don't do too well with accurate uncertainties in the sense that we can take our model and we can test it on out of distribution data, which is way different from the observed region. This gives us confidence intervals of our predictions, but this is not the same thing as rigorous uncertainties. With these observations, we don't really have rigorous uncertainties, and therefore it's also really hard to propagate them through the model. Third, there's no free lunch, right? So building the training set and training the model are not trivial. And a lot of our time is spent running the simulations, post-processing them, producing this labeled training set. Running the model, once everything is trained, is super fast, less than a day, minutes, hours. But there's still a lot of back-end effort that goes into making this work. And at the end of the day, the results are still dependent on your training set. So this brings us to a possible solution. What about unsupervised machine learning? That is, our identifications are entirely driven by what the data looks like and its statistical properties. And so this is exactly what Josh is going to talk about in his talk next. So I can answer a few questions now, if you have questions, before I hand it over to Josh for his second part. I can't see the questions online, so if there are questions, you have to let me know. Questions in the room? Yes, Nina?
What, and I guess Josh will go more into this. What's the difference between supervised and unsupervised learning in machine learning?
So in the supervised learning, in the training set, we have labels. So we know exactly what we're looking for. In the unsupervised machine learning, we don't have labels. So in a sense, you're looking for interesting features within the data, but you don't go in with a very clear definition of what those might be. Yes.
Is any part of the model like physics informed, or is all the training loss based solely on the statistical properties of the simulation data?
It's just a mean squared error function. It is physics informed in the sense that we put the physics in the simulation and into the training set, but we're not explicitly coding it into the loss function, for example.
So in the data, there is a degeneracy between the spatial distribution along the line of sight and the velocity. So does CNN learn that? Apparently, when you estimate the mass properly, I assume that you're learning that, right? Or are you feeding like the velocity from the simulations to your CNN as well? Or is it just like the emission lines?
So it's all one cube. So what the model is doing is making a prediction for each voxel, and each voxel is the emission at a particular velocity channel at a particular point in the cube. So it is learning for each voxel to separate what emission is coming from the background thing we don't want, the cloud, versus the feedback. And it's learning that relationship from the simulations where it's seeing in a connected way. None of these voxels are independent, but they're part of these larger structures. And so it's learning how this information is stored in these cubes and how to pick it apart given our labels. It's key.
And so how circular is this in the sense that the simulations are not really a true representation of reality? So how biased do you end up getting as a result of that?
Yes, right. So that goes back to the question, right? So The answer is right, you don't, you're always gonna be limited because you can never simulate the universe exactly. So the best you can do is put in all of the physics, and try to match the conditions as closely as possible. But that's always going to be a problem, right? It's always gonna be a limit. So, you know, how much do you trust the simulations? How much do you trust that you just generally understand the mean properties of the region you're trying to identify features in? Does that answer?
Yeah, and I guess my other question is it possible, I guess this speaks maybe to the amount of time that it takes to run the simulations, but presumably you can turn physical processes on and off and learn which physical processes are important to actually get good representations of the real data.
Yeah, that's a good point. You can do that. We haven't explicitly done that here. What we have done is we have looked at the impact of chemistry on it because there's some different assumptions and abundances, for example. But mostly we use this as confidence intervals to say, all right, if we had this underlying chemistry and these assumptions, we would get this slightly different estimate for the momentum, for example. Online question?
I think it's from me, Adele. Thanks, Stella, for showing some nice data and some nice results. I have a question about the supervised learning and how you decide the exact labels for each basically voxel of gas, I'm assuming. So, for example, how does a gas particle get labeled as either outflow or bubble? Because it seems like actually in the universe, it's all mixed together.
Yeah, that's a great point. So in the simulations, we're tracking all of the material. We're tracking the wind material, we're tracking the outflow material. So in a sense, we're tracing it already in the simulations. So the simulations come with a set of labels that for each cell, we know what fraction that cell is that's in there is due to stellar wind material and what fraction was part of the background cloud. So if you're an observer, you can't tell the difference, right? But in the simulation, because we're actively tracking that, over the course of the simulation, we have that information to act as a label when we're constructing the training set.
Thank you.
Please, one.
One more question? Okay.
Yes, this is Stephanie. Thanks, Stella, for your great talk. Super interesting. And I don't work at all in this field, but I was curious to whether this could be extended to similar phenomena at larger scales. And I'm thinking specifically of outflows around supermassive black holes, because we also have molecular gas observations, even of CO, and it can look quite similar. So you typically have two directions of the outflow in the molecular gas. And I feel like it might be even easier because usually only one, because it's one supermassive black hole, like an AGN, and it's one outflow. But do you know if there's any similar effort or if your approach could be adapted for different scales like that?
I think it could. The underlying network is totally agnostic about the physics. So all of that's in the training data. So provided you have labels, provided you have simulations that you can attach labels to or observational data labels, you can certainly do that. It's hard to do it with hand labeled data because we don't have enough observational data to do that or enough volunteers unless we're doing citizen science, which some people have found very useful. But for simulations, you might use something like, I don't know, the fire simulations to run with Gizmo, and that might have some of the same tracer information that we have for our smaller scale runs and that could be used for galactic outflows. All right, let's wrap up now. So I guess thanks everyone for coming to the first seminar. And hopefully we'll see you back here in 2 weeks for the next talk. Thanks everyone who joined us online, and feel free to reach out if you have questions. I'm happy to answer later, have other discussions. All right, thanks everyone.